small class. But let me start with the announcement. So there is a exam tomorrow. I don't know if you probably know that. It's going to be in Bartlett Hall, room 65. And as I had mentioned, it's a closed book, closed notes exam. But on the weekend, I had posted a note on Piazza saying you can bring a one-page handwritten, okay, cheat sheet. You can write whatever you want on it and bring it. So you don't need to. If you think something is hard to memorize or something, you are welcome to write it on one page of paper, bring it, and then you have to attach that to the exam book and turn it in, right? So other than that, you can't bring any other material. Okay? So one page cheat sheet we will allow, so you don't really feel the pressure to memorize lots of things. All right. So that's the first announcement. The second thing I wanted to mention is I'm hoping to hand out the homework solutions and the homework grades, just so that you can see how you did. And as I had mentioned on Piazza also, the exam questions have similar flavor to homework questions. So by this time you should have some idea of what type of questions to expect. So for that reason, I'm making sure that we'll try to get the grades out today. Sample solutions we'll post shortly after class to Canvas, so you should have that. Okay? So if there are any questions, you should let us know. The last thing is, once the exam is done, you still have the lab due. Remember that is due on the 1st of every month. So the lab is going to be due 1st April, and the last lab is going to be due May 1st. All right? So keep all of those things in mind. So what we'll do today is to continue the discussion from last time. If you remember, last class we were talking about clock synchronization. We talked about GPS, and towards the end of the class, we were talking about this notion of a logical clock that allows us to reason about ordering of events without actually using a real clock, without assuming any clock synchronization. Okay? And towards the end, we said that what logical clock gives us is, if there are two events that have occurred in a certain order, the timestamp that the logical clock algorithm gives it will make sure that the one that happened before has a lesser timestamp than the other. Okay? But what it doesn't have is the opposite property, where by looking at timestamps we can reason about ordering of events. That we'll look at today using vector clocks. And then I'm going to talk about another technique for solving a slightly different problem, which is called distributed snapshots and termination detection. And towards the end of the class, if we have time, we'll start talking about leader elections. Right? So that is the agenda for today. Let's start with the Lamport's clock. But before we do that, I want to give you a new concept which we have not completely discussed, which is total ordering of events. Okay? What we discussed with logical clocks allows us to give what's called a partial order of event. Certain events that are ordered by message passing get ordered, okay? Because the send of a message is always happens before the receive. All the events before the send and all the events after the receive get ordered. But any other events that are occurring in these processes are not going to get ordered. So here are some examples here. The y-axis is time. Okay? There are three processes, P1, P2, P3. They all have events A, B, C, D, E, F, G, H, I, and so on. Okay? So the lines that go between processes are messages that are going back and forth. So you will see that B and F are ordered, because B is the send and F is the receive. Message must always be sent before it's received, so that gets ordered. As a result, event A, which is before B, and all the events after P2 get ordered because of transitive properties. Okay? But if you look at E and C, okay? E is in process P2 and C is in process P1. They are not ordered because there's no message that has gone from P2 to P1 that allows us to order this. So from our perspective, they are concurrent events. We cannot say which one has occurred before which other one, because there is no real timestamps here. So we are not using real clocks to assign timestamps, so we don't really know what order they occurred. So this is going to give us a partially ordered relationship. Right? Now, if you want to take a partially ordered set of events and just make it totally ordered, we can just impose some arbitrary tie-breaking rules that say, if you have partially ordered events, use some way to order those events. So what we will now do, we will essentially assume that numerical IDs that you have, logical clock IDs that you have assigned to events also dictate for a total order. Okay? Even though they have not really total order, we are just going to say when we don't know, we'll arbitrarily assume some order. Okay? And so that's the order that we will assume, even though that may not be the real order because we don't really know, it's only a partial order. Okay? So in this case, and furthermore, we will append the process ID to the timestamp. Okay, so the timestamp here, which were 1, 2, 3, 4, will become in process 1, P1, will become 1.1, 2.1, and so on, because you appended the process ID, okay, after the decimal place. Okay, so now the clock values are essentially real numbers. So this is clock value 1.1, 2.1, 3.1, and so on. Okay, here also you do the same thing. So you will see the clock values become 1.2 to 3.2 and so on, and 1.3. So this gives us a tie-breaking rule. So if there are two events with clock 2 in two processes, okay, so you would not know what the ordering is. Okay, but now because one of them will be 2.1 and the other one here, let's say, is 2.3. You will say 2.1 is less than 2.3 numerically, so we'll just assume that's the order. Even though you will see that 2.1 and 2.3 have no relationship, there is no message passing between those two processes for us to know the real order. We just made a tie-breaking rule and just assigned an order. Okay? So you can take Lampert's clocks, okay, which give us a partial order, and then you can just use this technique that just imposes an arbitrary total order. It's not a real total order, because we don't know the order for certain events, but we just made up a rule saying this is the way we are going to order events, and all processes agree on this, so we just derived an order. Okay? So this is a simple technique where you can take the logical clock approach, okay, and then assign an ordering group. Now you might say, why are such ordering important? So here is an example of why the ordering might be needed. Okay? So this is an example of a database. Okay, so here we'll get to totally ordered multicasting later, but let's just think about why total ordering even matters. Okay? So here is an example where you have a database. Let's say it's a bank database. Because the bank has important information, they make a copy of the database. So there is a replica. Okay? So here you have one copy, here is the two disks represent the two copies. Okay? And let's say users are making queries on the database or making updates, maybe they're depositing money in their account or withdrawing money or something like that, which updates the database. Okay? Because the database is replicated, you want the state of the database to be consistent across the two replicas. You don't want one replica to have some different data than the other replica, then your database has gone out of sync. You don't know what is the actual data that you should trust in the two replicas. So the two replicas have to be consistent. Okay? The way we are going to enforce consistency is to say that each update that you make to the database, okay, or all the updates that you make to the database have to be in the same order on both of the two replicas. Okay? So that if you start from a certain state, if you have the same set of requests that you process in the same order, you will end up with the same state by definition. Right? So if you start with a certain state and you say deduct $10 from account 1, okay, you do that, and then the database are again in the same state after the replica. And you do another query, they will be in the same state. But if you do things out of order, you may go out of sync. Okay? So for example, if you say, I withdraw the money first, and then I calculate the interest for the month on the remaining balance, okay, that will give you some state. But if you do them in the opposite order in the other database, you first calculate the interest and then withdraw the money, you may have a different interest that you end up with, and so the bank balances will differ in the two cases. Okay? So you always want, when you have database replicas, for the request to be processed in the same order. Okay? Now with that background, let's now look at the two replicas and see what is happening. There are two users that are shown there. Okay? The user to the left is closer to the first replica but further away from the second replica. This user is closer here and further away from the rest other one. Okay? So let's say they both issue some update to the database, more or less at the same time. Okay? Every query is sent to all replicas because you have to do the same operations on all the replicas. But it's so going to happen that this user's query is going to arrive here first, and this takes much longer over the network to go here. Okay? And this user's query is going to arrive at the second replica first, but takes longer to arrive at the second replica. Okay? So if you just look at the order in which requests are arriving to the database, these two requests are going to arrive in two different order at the two database. In particular, users 1 request will arrive here first, and users 2 request, even though it was issued more or less at the same time, took longer to come over the network, so it arrived later. Okay? And it's going to arrive at the other end in the opposite order. Okay? So now if the database simply processes requests in the order in which they're arriving, you will go out of sync because now you got requests out of order. Right? So you don't want that to happen. Even if requests are arriving out of order, you want to keep the requests or reorder the request so that you process them in the same order. Okay? This might require you to delay a request before another request that should have been processed first actually arrives. Maybe it's still in transit. So to do all of this, you need to have a total ordering of all the requests in the system. Okay? So this is where the total ordering concept that I mentioned has to come in. So if you assign a total ordering to your queries, okay, and you process the queries in whatever order is dictated by the total ordering, you are going to be good. Okay? So the Lamport's clock technique that I talked about, okay, can be applied here. I'm not going to show you all the details. This was just an example to convince you why total ordering is necessary in some cases. Okay? Because you may have replicas that are far from one another. Okay? Messages take different amounts of time to traverse the network, so they may arrive out of order at different replicas. And processing things out of order, if they are replicas, will make things inconsistent, make the state inconsistent. So you don't want that to happen. Okay? So I'm not going to go into how you can use Lamport's clock to do total order multicasting right now. We'll get back to that later. If you're curious, there's also further details on this example in the textbook, but we will get to this. Okay? What I want to do instead is to this is what we'll skip today, we'll get to this later. What I want to do today instead is to talk about vector clocks, okay, which is essentially the generalization of Lamport's clocks. Okay. Just as a recap, we talked about Lamport's clock last time. Okay. I said Lamport's clock are a simple integer. They have nothing to do with the real clock on your machine. Okay. Every time a process processes some event, it's going to take its integer. It's going to increment its integer by 1. Okay. Every time a process sends a message to another process, it's going to piggyback its clock value. Okay. And when a process receives a message, it takes the max of the clock value that came on the message, max of its local clock, max of those two values plus 1. Okay. That's our time stamping algorithm. Okay. And we said what this gives us is if event A has happened before event B, that arrow there between A and B is the happened before relationship, then the clock value that you assign using this algorithm will be such that clock value of A is less than clock value of B. Okay? A has happened before B, so A has gotten a lower logical timestamp than B. Okay? But what we also said is the reverse is not true. Okay? If I give you two clock values and you look at them, you can't actually reason about this unless you impose some total ordering that I just talked about. Okay? You didn't do that. If I just gave you two clock values, let's say one has clock value 2 and the other has clock value 3, you can't say 2 is less than 3, so the event with timestamp 2 has happened before the event with timestamp. Lamport's clock does not guarantee you that property. Okay? Instead, we want to generalize Lamport's clock with an algorithm that actually guarantees that property. If I give you two timestamps, two numerical timestamps, and you are able to say one is less than the other, it's guaranteed that the event with the lower timestamp has happened before the event with the other timestamp. Okay? That property is called causality. Okay? So essentially we need to maintain causality, and here causality will mean that if A has happened before B, we say A is essentially causally related to B. Okay? There are other causality properties we'll get to later. Just as one example, one is called causal delivery. If you're sending two messages, M and N, okay? And if the send of M, event that represents the sending of the first message, has happened before the event that represents the sending of the second message, then the receipt should also happen in that order. But if you send one message before the other, receive them in that order. Okay? That's called causal delivery. Okay? But there are many other properties. Okay? Right now we are just worried about time stamping. We are not worried about enforcing causality or anything like that. So in other words, we need a time stamping mechanism such that if the timestamp of A is less than timestamp of B, then A should have causally preceded. A should have happened before B or causally preceded. Okay. So let's see how to do this. Okay. This is going to give us a new algorithm. It's a generalization of Lamport's clock. It looks very similar with some very small differences. Okay, we'll now call them vector clocks. So it's a generalization of logical clocks. Okay, so every process now, rather than keeping one integer, is going to keep n integer. Okay? And it's a vector of n integers. The ith value of that vector is the Lamport's clock of that process. Okay? But you are now keeping track of other clock values as well. Okay? And here is how it's going to work. Okay? Whenever, so let's say each process still has to track local events. So if there's a local event on process I, it's going to increment the ith value of its vector. Same as Lamport's clock. Whenever there's a local event, you increment your clock. Okay, you increment the integer. Here you are now a vector, and for process I, it's the ith element is your Lamport's clock. So you are going to increment the ith element. Okay? When you send a message, okay, you are going to piggyback the entire vector clock. Okay? In the previous case, you piggyback one integer. Now you are going to piggyback a vector. Okay? And when you receive that message, you are going to take the max of two vectors, okay, which means that you compare each element pairwise. So this is an array of n integers. You compare the first value of the two arrays, second value, take the max of each. Okay? That's the max of two vectors, and then you increment your ith one. Okay? So it looks exactly like Lamport's clock, except that rather than doing this for integers, you have done this for vectors. Okay? So that's all. So for local events, you increment the ith value of your vector. Okay? Then a message, when you send the message, you send the vector. Okay? When you receive the message, you do pairwise comparison of each element and do the max, and then you increment your ith value. Okay? And that's it. Okay? And now you can show, and I'm not going to actually give you a formal proof, you can show that if vector of A is less than vector of B, then A causally precedes B. Okay? And I'm going to show you this by example, not like a formal proof, so that you understand how this is actually working. Okay? So I actually hand drew this, but you can probably understand what's going on. So there are three processes, P1, P2, P3. Okay? So the vectors have three elements. Okay? All processes start with 0, 0, 0. Okay? So here is what P1 is going to do. Every time there's an event, it's going to increment the first element. So this will go from 1, 0, 0, 2, 0, 0, 3, 0, 0, and so on. Okay? P2 is going to increment the second element. Okay? So this one will go as 0, 1, 0, 0, 2, 0, 0, 3, 0, and so on. Okay? This one will increment the third element, 0, 0, 1, 0, 0, 2, 0, 0, 3, and so on. Okay? That's what you do for local. Okay? Now let's take message M1. Okay? It's going from P1 to P2. Okay? So you have to send the vector clock in. So you will send 2, 0, 0 along with M1. Okay? So you will take 2, 0, 0, and then the vector here is still 0, 0, and 0, 2, 0. The max of the two is going to be 2, 2, 0, because you are doing pairwise comparison and taking the max. Okay? So you take 2, 2, 0, and then you increment the second value, that gives you 2, 3, 0. Is that clear? Any questions here? Okay. And so on. So here is another message M2. Okay, so this one goes with 250. Okay, so that's 250, and it comes here, the vector is 0, 0, 4. So you take the max of the two, that gives you 254. Okay, and you increment the third element, that will give you 255. So you take the max of the two, and then you take your element, okay, 255, and so on. Okay. That's your algorithm. That's the timestamp. So now all of those events have timestamps. Now the claim we are making is, if you take any two timestamps and you compare them, okay, and if one timestamp is less than the other, you are going to get the happened before relation. You can actually guarantee that the one with the lower timestamp is going to get a lower, it has happened before the other one. Okay? And you can figure this out. Okay, let's just take all the messages along that send. Okay? So take 1110, that's less than 200. So that clearly has happened before that, it's execution only. Okay? Now you take 200 and 230, which one is less? Here's the first one. Send has always happened before the other one. Clearly the send has gotten a lower timestamp. So if you say 200 is less than 230, I know that the one with 200 has happened before the other one. Okay? Yes, question.
When you're doing the comparison, you're taking the norm of the vector, like you're comparing the magnitude of the vector?
No, so question, that's a very good question, because I have not defined what comparison is. I was going to get to that. Okay, so question is, what does it mean to compare two vectors? Okay, So I have not defined the less than relationship on the vectors. You're not doing the magnitude. You are essentially saying vector A is less than vector B if every element of A is less than or equal to every element of B, and there's at least one element of A which is strictly less than. Okay? Which means if you given two arrays and you say first array is less than the second array, you have to have every element in the first array to be less than or equal to the second one, and at least one has to be strictly less than, which means that there has to be all elements have to be less than or equal to, and one element has to be strictly less. That clear? What I said? Okay. So basically numerically the values of each value in each ith element has to be either less than or equal to. That's what we mean by less than relationship, and at least one has to be strictly less than. Okay? And if you can't have that relationship behold, then you basically say the two vectors are not comparable, and we'll see what that means. Okay? Just as a second. All right. So if you take everything along the send path and the receive path, you will see the events have gotten ordered. But now let's take two events that we can see are concurrent. Okay? Let's take this one 300, and you take or E is 400. Okay, and event D is 020. Okay. So if I just give you these two vectors 400 and 020, which vector is less than the other one? 040? Yeah.
So does that mean that it's now kind of, it goes the other way around as well? Like if you just compare two vectors, you can tell that one happened before the other.
Yes.
So it's an if and only if.
Yes. In this case, it goes both ways. But what I'm asking now is, I give you two vectors, numerical, right? It's not, it's 400 and 020, and I say compare them. Is the first vector is 400 less than 020 or the other way around?
Neither.
It has to be neither, because it's not like every element of 400 is greater than this or the other way. Okay? So these two vectors are not comparable. Neither is A less than B or neither is B less than A. So that tells you that these two events are concurrent. You cannot order them. Because I said if vector of A is less than vector of B, A happened before B. Okay? But if those two vectors are not comparable, you are guaranteed that neither has A happened before B nor has B happened before A. They are concurrent events, which is true here, because you see that there is no message going that way. Right? So this event has not happened after that event or vice versa. Okay? Is that clear? Why? Any questions? Okay. So the happened.
Is this clock also distributed among like different processes?
Is the clock distributed among different processes? Is that your question? So the clock is a vector that each process maintains. It's not distributed. So P1 has its own clock, P2 has its own clock. So think of each process keeps a local array. That's your clock, array of integers. Okay? And you just increment it based on the rules I just mentioned. So you're not going to distribute it in the sense, of course you send it back and forth, but each process has its own clock. Okay? So you can compare, okay, A and B. Okay? So A is here and B is here. So you know A has happened before B. You see the vector of A 100 is less than 240, strictly less. Okay? A and C. Okay? So A is here and C is here. 100, 256. Okay? Clearly 100 is less than 256, and you will see that A has happened before C. Okay? Can you explain why A has happened before C? There's no message going from P1 to P3.
But there is a message going from A to B and then B to C.
Okay, there's a message going from A to B and B to C. Remember, the happened before is transitive. Okay? So you will say that A has happened before the send. The send has happened before the receive. This receive has happened before that send. That send has happened before this receive. That receive has happened before C. Okay? And transitive property holds. If A has happened before B, B has happened before C, A has happened before C. So you follow this chain. So you don't need an explicit message between two processes to figure out the happened before relationship. It still holds based on indirect messages that go through a third process. Okay? So it still gives us the right property. So that A has happened before C. Okay? So now you can compare A and D, 100, 020. not comparable, right? Because only this receive has happened before A. Anything before the receive you can't see. Okay? So you'll see 1 0 0 0 2 0 not comparable. E and D I already talked about, not comparable. B and F. Okay. So this is B, 2 is 4 0, F is 0 0 2. Okay? Again not comparable. Okay? So it's not a proof, but at least now you should get an idea of why the vector clock is giving us the reverse property as well. Right? Any questions on this? Okay. So you can actually now use vector clocks to essentially delay message receipt so that you can process messages in the right order and so on. And here is an example of how you can enforce causal communication. Okay? This is going to go back to the database example that I was talking about as well. Okay? So here are three processes, P0, P1, P2. You will see that there are some vector clocks. Okay? So here's an example of what has actually happened. P0 has sent message M, but it's broadcast that message. So that message goes to both processes at the same time. Not to one, but it goes to both. Okay? So it is received by P1 here. Okay? And then P1 is going to send another message out. Again, it's sent to both. All right? And we have a case here where P1's message arrives at P2, okay, before P0's message arrives. P0's message, you see, is taking a long time. It arrived at P1 quickly. It's taking a long time to arrive to P2. Okay? But P1 maybe is closer, so P1's message has arrived. Okay? But when P1's message arrives, it comes with a timestamp 110. Okay? And what can P2 see with that 110? It will see that 110 says that P1 has received at least one message from P0, which is why that first element is non-zero. Okay? But you know that you have not yet received that message. All messages are, in this scenario, being sent to everyone. You have not yet received that message from P0 because you still are waiting for that. So you know that there is some message in transit that P1 has received, but you have not received. So you will delay the receipt of this message until that other message that's in transit comes. So that is why you see that this message hops. So you wait for this message. Now you know that message has arrived. Then you take the delivery of the other message. So by simply comparing timestamps, you can even tell what messages in a scenario of messages are broadcast, of course. Okay? So you can tell what messages are in transit and which ones have not been received. Okay? So going back to that database example, you can use vector clocks, and if you get a message out of order, you will say that other replica seems to have gotten this message. I have not yet gotten it, so I should wait, because otherwise if I process this message, I will process messages out of order. Okay? If you want to enforce causal communication. Okay? Just a simple example to show what you can do with vector clocks among many other things. Okay? You can enforce causal communication as one of the many use cases. Of course, you can reason about ordering of events, no clock synchronization necessary, and so on. Okay? Any questions on this? Yes?
What if P2 doesn't know that P0 is broadcasting a message?
Okay. What if P2 does not have P0 is broadcasting? So if messages are not broadcast, this information is not helpful to P2. Okay? Just because I got a timestamp on a message of 110, all that tells me is P1 has received a message from P0. Okay? So if messages are one-to-one, this is not going to tell me anything. It just tells me P0 got a message from P1, P1 got a message from P0, and I got a message from P1. That's all it tells you. Okay? Only in scenario where you are doing what is called multicast or broadcast, do you know, okay, this is actually the case, that P0 has sent a message, it's reached another process, that process sent me a message later on, and I'm yet to receive the first message that P0 got. So that you can tell in a broadcast situation. Okay? So this example is very specific to broadcast or multicast, not for one-to-one message passing. This is not helping us anymore. Yes, question.
The problem that you set up earlier about synchronizing databases, is this type of broadcasting semantics used similarly, except that instead of it being processes, it's databases, or
Yeah.
is that a separate problem?
So the question is, the database scenario that I mentioned, can it actually use this broadcasting technique? Okay, so indeed you can use it. Okay? Real systems seem to still use real time stamping and clock synchronization. But you can use vector clocks to enforce exactly that. You can say, I can guarantee you an ordering of events and things of that. So yes, you can certainly do that if you wanted to. Yes, question?
Kind of implicit assumption here is that your messaging system is perfect, because if P2 is postponing and the message never arrives or gets delayed or something, you're
Yes.
effectively knocking a node out of the entire system.
Yeah, so good question. Question here is, we are assuming that messages are not lost. Network is delivering all the messages. Okay? The message that let's say P0 message to P2 gets lost. Now, the network just loses it, because networks drop packets, I presume you all know that. And so network drops the packet, as message doesn't arrive, P2 will be waiting for it forever. Right? That is indeed true. So the assumption here is a reliable network. The network always delivers that message. Okay? Now that's not a strong assumption, because as you know, TCP guarantees you that. Okay? TCP by itself will track what messages have been received and retransmit. Okay? So you can just assume that all these messages are going over TCP and that condition is satisfied. But yeah, the abstract assumption is messages are not getting lost. It's a reliable network. Every message that is sent is actually delivered. It may take a long time to deliver because the delay could be large, but it is delivered. Okay? Is that clear? Okay, good. So that is causal communication. So we are going to switch gears. We are done with logical clocks, we are done with vector clocks. I'm going to now talk about a different problem in distributed systems. This one is called essentially distributed snapshots. But to discuss what this problem is, first I'm going to define a new term, which is called the global state of the system. Okay? So what is a global state of a system? Okay, so the definition of global state is the global state of a system, and that's defined at a certain time instant. Okay? So global state of a system at time t is the local state of each process at time t. And the local state is simply the memory contents of that process. Okay? So the global state of the system at t is the local state or the memory contents of every process at time t, plus all of the messages that are in transit between processes. Any message that has been sent but not received somewhere on the network. Okay? Somewhere propagating on the network, it's in progress somewhere. Okay? So local state of every process and all the messages in progress, messages that have been sent but not received. Okay? So that collection of things is called the global state of the system. Okay? Now why does this matter? What does this have to do with anything? So essentially the reason you want to know the global state is there are many problems that depend on it. Okay? The simplest problem is failure recovery, but you can also use this for distributed deadlock detection and so on. Okay? So what is failure recovery? So let's now take n processes in your system. Okay? Let's say one of the process crashes. Okay? What are you going to do? Okay? You can say I will just restart that process, but if it hasn't preserved any state, then it's going to start with some arbitrary state. It can't participate in the application. Okay? So think about, let's say, to make this more concrete, let's say you're running a parallel simulation. Okay? So you basically start n processes, each of them is computing something, they're all communicating, they're trying to simulate some larger system. Okay? Let's say one process crashes in the system. Okay? So one option is you terminate all the processes and restart the simulation from the beginning. Okay? Now that means that all the work that the processes did before this process crash is wasted. Okay? You say with the simulation, if any process crashes, I terminate everything, I restart from scratch. Okay? Another thing you could do is to say every so often I'm going to let the process take its intermediate results and write it to disk. Okay? Now if a process crashes, I'm going to terminate all the processes. I'm going to go to the most recent set of intermediate results. I'm going to load those results in the process, all the processes, and start from that point. Okay? This means that I don't have to go back, what is called roll back to the beginning. I am actually going back to the most recently saved state of the process. Okay? So periodically you're saving a state so that if there's a failure, I just go back to the most recent. It's like taking backups, right? Same thing. You can every night you take a backup. If your disk dies, okay, you can go to the previous backup and get it. Anything you did after the backup is lost, but at least you got everything in that previous backup. Same thing. Okay? Your state is like taking a snapshot or a checkpoint, and you save your state and you recover. Okay? But the question is, how do you do this consistently? Okay? That is essentially what you need to store is not just your state, but you have to store what's called the global state. Okay? And we'll see why. Here is the case. Okay, so essentially, if you take a snapshot, we need a consistent global state. Okay? And let's look at some examples, and I will explain what a global state is. Okay? So taking this, storing this global state is easy if you have perfectly synchronized clocks. Okay? If the clocks are perfectly synchronized, you would say at the beginning of each hour, all processes should freeze. They should write their memory contents to disk, and they should continue. Then everybody has taken a consistent snapshot at exactly the same time. Right? So now I can go back to that whatever most recent saved state is. It's like taking backups at midnight. Right? So I kept it and I took and I rolled back and I restarted. But what if there is no clock synchronization on there? Right? The clocks on all machines are off. Okay? So you can't say at noon take a snapshot, because noon is meaningless because clocks are not synchronized. One clock, so one process might do it at 10:50 or 11:50, another one might do 12:05. So you took this snapshot or to save the state at different times. Okay? And now if the process crashes and you load these states that were actually saved at different time, it may not give you consistent results. Because you're saving them at slightly different time. So you want to make sure they're consistent, even though clocks are not synchronized. Okay? So how do you do that? So that's basically going to give us this notion of a consistent cut. Okay? We'll say we can tolerate processes saving their states at slightly different time, so long as there is consistency. And what does consistency mean is what we are going to define. Okay? So here are two examples. Okay? There are three processes in each example, P1, P2, P3. Okay? X-axis is time. Processes are sending messages to one another. You'll see messages M1 and M2 so on. Okay? The dotted line, okay, is essentially the time at which each process has chosen to save its state. Okay? And you'll see the dotted line is intersecting the processes at different points in real time. Okay? This is because clocks are not synchronized. If the clocks are perfectly synchronized, this dotted line would be a vertical line, okay, that intersects them all at the same time. But clocks are not synchronized, so noon might mean this time here, this other time here, and the other time there. Okay? So they're taking it different time. Okay? But we'll say that this will still be okay if this is basically what's called a cut, because it's cutting the processes at some point in time. That's the time where you store your state. We'll say it's consistent if the following properties are true. If there are any messages being exchanged, the send and receive of the messages either has to be completely on the left of the cut, completely on the right of the cut, or you can have a case where the send is to the left and the receive is to the right. But the opposite cannot be true. You can't have a receive on the left and so here there's process M1. Okay? That's completely to the left of the cut. That happened before the state was saved. That's what it means. That's okay. Okay? Your process M2, that's completely to the right of the cut, which means that that process, if you restart at where the cut is, that process will be, that message will be sent after the process restarts from that point. That's also okay. And you will see M3 intersects the cut. The dotted basically is intersecting the dotted line, and you'll see the send is to the left. Okay, the send of M3 is to the left of the dotted line, and the receive of M3 is to the right. Okay? That's also okay. That's a message in transit. That's a message that has been sent but not yet received. That is why it's being intersected by the cut. Okay? And that's okay. So long as you save M3 as part of your snapshot, we are going to be okay. Okay? So to understand what is consistent cut, let's look at an example of an inconsistent cut. So that gives you what consistency means here. Okay? Same example. Okay? But now the snapshots or the checkpoint is being done at different times. Okay? The dotted line looks different from there. Okay? M1 is to the left of the cut. That's still okay. M3 is now to the right of the cut. That's fine. Okay? But look at what has happened to M2. Okay? The receive of M2, the receive event is to the left. The send event is to the right. Okay? So what this means is the receipt is basically has already, the process P3 has already processed M2. Okay? So it's already processed it, then it saved its state. Okay? And P2 has saved its state at a point where it's not even sent anymore. So P2 saved it long before its state, then it started computing its at M2. Okay? P3 just decided to take a delayed snapshot, so it already processed M2 and then saved its state. Right? Now if you restart the computation at this point, what will happen? Right? This process P3 will start at this point, P2 is going to start at this point, and P1 is going to start at this point, and they'll start computing. Okay, and P2 will compute and resend M2. Because it will basically start from this point, it will execute something and some event will cause M2 to be sent. Okay, and P3 will get a duplicate version of M2. It already processed it. Okay, so you will get that message twice and that will be inconsistent. Okay, because the receipt is actually happened in this case is on the is the event that's happened before the cut and the send has happened after the cut. So that's inconsistent. That you don't want. So I said consistency means either the message is completely processed to the left, which means it's sent and received, it's done, it's never going to be seen. It's completely to the right, which means you restart from that point, both the send and receive will occur if you restart. Okay? Or it's a message in transit. Okay? But you can't have a processed message that's not being sent. Not a question, yes.
Would it not be possible, say, for each message to be sent with a unique ID, and for, in the case of B, for P3 to kind of update its reception time if the same message has been sent again to account for the inconsistent state and solve the problem?
Okay, so question is, can you not send a message with a unique ID so that you can track whether the process is already sent or received the message, etc. You could do that, but my point is, why even do that if you can find an algorithm that only gives you a consistent cut? Then you don't have to worry about this, right? You will never have this case to begin with, so you don't need to worry about it. So our goal is, in the absence of clock synchronization, find a way for each process to save its state so that you still always end up with a consistent. Okay? If you have clock synchronization, this is a trivial problem. It's not worth solving. Okay? Every process can pause at exactly the same time and save its state. So you'll never have a case where you have an inconsistent cut. Okay? Only because you're saving your state at different times, noon here means something else. On each of these, you are saving them at slightly different points in real time. Okay, you have this problem. You got to make sure your cut is consistent. Is this clear? Okay. So how to do this is that this is just a concept. We haven't seen how to solve the problem. Right? So let's see how to solve this problem. Okay. We'll use simple TCP to solve this problem. But first, let's try to take an example. Okay? It's called distributed. This whole thing is called distributed snapshot, which means at the end of this algorithm, every process would have saved its memory contents to disk. You would have captured every message that's in transit. Okay? And then you just have to restart from that point on, and then your entire computation will start, and you don't need to worry about starting from the beginning. Okay? So what's a distributed snapshot? Okay. Let's take an actual physical example of a snapshot, and then you will try to understand what is going on. Okay? So let's say that you want to take a picture of the sky, you take a photo of the sky. Okay? But let's say the phone, your camera on your phone does not have an angle that can capture the entire sky at once. Okay? You point it to the sky, it only looks at part of the sky, not the rest. But you want to capture a photo of the entire sky. So what are you going to do? Okay? You are going to take multiple pictures, right? And then you're going to basically make a panorama by stitching them together. Okay? That's what you will do. You'll just take a picture. It's like taking a panoramic picture, but you'll take multiple snaps. But you want it to be consistent. Okay? What does consistency mean? In this case, because the pictures are now being taken at different times. You take a picture here, then you take a picture here, you take a picture here. You want to get a consistent view of the sky as it existed. Okay? What does consistency mean? Okay? Let's say there are some birds flying in the sky. Okay? You want to get a consistent picture. What does that mean? That every bird has to appear, if there are n birds, okay? Every bird has to appear in some one of these pictures you have taken. So you captured all the birds. Okay? You don't want a bird to not be captured in any picture. Okay? So let's say you're pointing your camera here, there's a bird right here. You move the camera here, the bird has already flown to the other. So that bird has disappeared, not in any picture. Okay? So that is basically like a missed message. Okay? You don't want the other thing to happen either. You take a picture of the thing here, some birds appear, you point the camera here, a bird flies into the next frame. Now you captured that bird twice. That is our duplicate messages. You don't want messages to be missed. Birds here are messages, right? You don't want a message to be missed. Okay? Neither do you want a message to be captured twice. Okay? So if you do all of this, okay, and then the picture of the sky is essentially like our memory state. So if you capture the entire sky and you captured everything consistently, you got a consistent view. Okay? You didn't miss anything important that was happening. Okay? That is a distributed snapshot. Okay? Same concept, okay? Different idea, but same concept of what I talked about with messages. Okay? Because you're taking pictures at different time, you are going to take snapshots at different time. You don't want to miss any messages, and you want to capture all the messages in transit. Okay? So here's how it's going to work. Okay? So I'm going to show you a very simple technique that will allow us to do this. Okay? Now the basic idea is very simple. Okay? Let's say there are n processes in the system, they are communicating with each other. Let's say they are using TCP/IP to communicate. Okay? There may be some open sockets between these processes, they are just sending messages back and forth, they are doing local computation. Okay? Any process can start the snapshot algorithm. You can say, it's time to take a snapshot. Okay? And when you do this, that process has to first take its entire memory. It may pause for a second. Okay? Take its entire memory contents, write it to disk. Okay? And then is going to send messages on all of its open TCP socket connections to anybody who has an active connection to it, saying, take a snapshot. Okay? So you're going to essentially send a message out saying, take a snapshot. Okay? And then if you have any incoming messages, you basically start saving those messages. Okay? Now, any other process in the system, okay, has to do the following. If it gets a message on any of its socket connection, they say take a snapshot. Okay? You will immediately pause and write your contents to disk. Okay? And you will send, meaning that process will send same messages on its active TCP connection saying take a snapshot, and then it will start recording on each of those socket connection every message that is coming in, because that's a message in transit. So every message that comes in, it has to save it on disk as well, in addition to processing it. Okay? And when you stop recording, when you get a reverse message saying take a snapshot. Okay? Because the second message on that channel that take a snapshot means to stop recording. Okay? So is this clear? I'm going to repeat this for just a second so you can understand what I'm saying. Okay? Any process, n processes. Okay? Processes are arbitrary TCP/IP. Doesn't mean every process has connection to every other process. Let's say processes have some connection to one another. Okay? Some TCP/IP connection. Any process can start the algorithm. Okay? When you start the distributed snapshot algorithm, you first write your memory contents to disk, and then you simply send a message on every active TCP connection saying take a snapshot. Okay? And when every other process that you have connection to gets this message, they will start the algorithm themselves. So it's recursive. Okay? You will do the same thing. You will write your contents to disk. You will send, now as this process will send take a snapshot messages to all other processes. Okay? And then because TCP connections are bidirectional, you send an outgoing message, all the incoming messages on that channel you will start recording to disk, you will start saving to disk. Okay? Until the process that you sent a message to sends a reverse message saying take a snapshot, at that point you will stop recording. Okay? So that's called a marker message. You send a marker message out, okay? And then you wait, you record on that channel until a marker message comes back to you. Okay? I'm going to show you an example and then we can discuss why this is going to give us anything at all. Okay? So here's an example. Here's process Q. Okay? That gray box is its memory contents. Okay? You will see that there is essentially a channel coming in, okay? And there are two channels going out. That's actually deceptive. The TCP/IP is bidirectional. This algorithm works for unidirectional ones also, but here we are not showing that TCP/IP is bidirectional. So you will see that here is a marker. Okay? This marker message initially means start recording. So when this message is received, this state is going to get returned to disk. You are going to send these marker messages on your outgoing channels. And a marker message essentially means, the first marker message means start recording. Okay? And then a second marker message on your incoming channel means stop recording. So let's see what happens when these two messages go out. Okay? Here is another process. Okay? So here now you have sent two of these, and then you have messages A, B, and C coming in. You are going to write out, in addition to the memory contents A, B, C, and then you wait for that marker message to come. So it comes after D, so then you stop. Okay. So as far as queue is concerned, okay, it basically is the memory state and messages A, B, C, D are now saved on disk. These are the messages in transit. That's your memory state. Okay. So marker message, the first time you get a marker message says start recording. Okay. The second time you get a marker message says stop recording. Okay. All the messages between the two marker messages are the messages in transit. Okay. Those are the messages that are in progress between the start and the end. So you have to save, in addition to memory contents, all the messages in transit. Is this clear, what I just said? Okay. Now that that is clear, let's say, why does this give us a consistent, the claim is this is going to give us a consistent cut. What does that mean? It means that at the end of this algorithm, every process would have saved its memory state. It would have saved all the messages that cross the dotted line, and only the messages that cross the dotted line. No message is going to be missed. Okay? And you'll never have a case where you saved a message that has not been sent. So you'll not get an inconsistent. Okay? So it's worth thinking a little bit as to what is happening. Okay? So let's just take a very simple example of two processes. Okay? The entire system has only two processes. Okay? So process A and process B, they have a single TCP/IP connection between them. Okay? Two processes, one connection. How does this work? Let's call them A and B. A starts this off. A writes its memory contents to disk. Okay? It sends a marker out. Okay? And then it is now start saving everything that B is sending to it is going to start saving to disk until B sends it a marker. Okay? So the marker goes out. Okay? Now B is going to get it at some point. Okay? What is B going to do? B is going to essentially start saving its memory content to disk, and it's going to send markers on its outgoing channels. Its outgoing channel is only one socket connection here. So its outgoing channel is the same channel that got the marker. So the marker goes back. Okay? And then when A gets the marker back, it will stop recording whatever B has sent to it in the meanwhile. Okay? Is this clear? So A is going to end up with a memory state and a bunch of messages that B sent it between it sending the marker to B and getting a reverse marker back. Okay? B is going to get the marker, the first marker from A, is going to save its memory content and is going to send the marker back. There is nothing for B to save because already got a marker on its incoming channel. Okay? That marker was an indication to start recording and stop recording at the same time. Okay? Marker essentially means start recording, but if it's the first time you get it, it also means there's nothing to record here, so it's you stop recording. So A is not going to send a second marker once A is done. Is this clear? So you can visualize how the distributed snapshot will work. So essentially you are going to end up, okay, with, at the end of this with some memory contents for each process, all the messages that are in transit, and you're done. There's no need to take the snapshots at the same time. You're taking them at different points in time whenever you get a marker message. There's no need for clock synchronization. Okay? You can take this state and restart A and B from this state, you will end up with a consistent state. You'll never, even though the snapshots were taken at different times. Is that clear? Any questions on this? Yes.
So I think it's clear in the case where there's two processes, but if there's n processes, do you need to wait for n-1 markers to stop? One for each connection?
Okay, that's a good question. The question is, if you instead of 2, you had n processes, do you have to wait for n-1 markers before you stop? Okay? So you stop based on not how many processes there are in the system. You stop recording on a channel based on how many socket connections you have open. Okay? Because you are not assuming I have an active connection to every other process in the system. A, let's say there are processes A, B, C, and D. A might have a connection only to B. Okay? B might have a connection to all processes. Okay? So we don't make any assumption as to what socket connections are open. All we assume is it's a connected graph, that every process, okay, is connected to every other process through some connection. Okay? So long as the graph is connected, not disconnected, okay? All you have to do is you have to send a marker message on your active TCP connection, and wait for a reverse marker message on that same socket connection to come back. And everything between when you sent the marker and when you got the marker back, you save to this. Okay? So you don't wait for n-1 markers to come back. If you have k open socket connection, you wait for k markers to come back. That's it. Right? If k is 1, then you just have to wait for 1 mark. So it doesn't matter how many processes there are. What matters is how many socket connections you have. Okay? So on every connection, you have to wait for a reverse marker, and then you stop recording on that connection. You might still continue to record on other connection until you get a marker on that each of those connections. Okay? Once you've gotten all of those markers back, you will completely stop. Is this clear? Okay. Any other questions here? All right, so we have a little bit of time, so I'm going to continue and talk about one or two more things, and then we will stop for the day. Okay? The next thing I want to talk about is what is called termination detection. Okay? So this is a slightly different problem from taking a distributed storage. Okay? What termination detection says is, let's say again there are n processes in a simulation. Okay? They are sending messages back and forth. Each message needs to be processed. And the question is, when do these n processes agree that the entire simulation job is completed and they can all exit? Okay? So essentially, this is a message passing system. So every time there's a message, there is work to be done. Okay? So the n processes have to collectively decide when the simulation is done and finish. It's not like you're processing some data and when you reach the end of the file, you say I'm done and I exit. Okay? The idea here is you basically send a message that causes some computation that might cause recursive messages sent to other processes, etc., etc. So what you will be done when there are no messages to be sent in the system and every process has finished its local computation. Then there's nothing more to be done. There's no new messages sent and your computation is done. Okay? Then there is no more computation that's ever going to occur in the system. Okay? So you want to detect this state autonomously between this group without any external input. Okay? So how are we going to do it? Okay? The idea is very simple. You basically have to ask every process saying, are you still doing some work or are you done? Okay? If any process says I'm still doing work, then you can't actually exit because that process might trigger some message. That message might trigger some other messages. Eventually you may get one more message to process. So you can't quit because there's a chance you may get additional messages. Okay? So the goal is to ask every process. Okay? And if any process says they are not done, you say, okay, I'm going to wait and perhaps there will be some more work to be done, and periodically somebody checks. And if every process says they are done, okay, then there is nothing more to be done in the system because a process done means they have finished their local computation, they are not going to send any more messages to any other process in the system. Okay? Now, you could have simply done a broadcast to all n-1 processes and said broadcast might be expensive because n may be very large. Okay? You might have n as a very large number. Maybe there are 10,000 processes doing a simulation. You don't want to send query 20,000 processes. Instead, we will essentially piggyback on all active TCP connections that are in the system and query that way. Okay? So this technique is called termination detection. So essentially, it is actually a part of the snapshot algorithm, but you don't need to worry about why it's part of the snapshot. You can use it separately. So what you will do is any process can start this algorithm to find out if all processes are done or not. Okay? And the way you are going to figure this out is you are going to essentially send messages on your outgoing channel saying, are you done or not? Okay? And then you wait for a message back. The message back could either say you're done, that means the process you asked said it is done, okay? Or the process will say continue, which means that it's not done, it wants to continue. Okay? And this is going to recurse. Okay? So if you get a request from a process saying, are you done or not, before you reply to that process, you have to ask all the other processes that you have active connections to, saying, are you done or not? Okay? And then wait for their responses. If they are all done and you are done, then you send back a done to whoever asked you. Okay? If any of the processes you asked to saying they are not done, they say continue, or you are not done, then you just say continue. Okay? So it's essentially you're constructing a query that is flowing through the network and asking every node saying, are you done or not? You aggregate the responses. If everybody says they're done, you are done, you tell your parent, I'm done. If anyone in your subtree is going to say, no, I still need to do some work, I'm not done, then you tell your parent that somebody in my subtree says they need to continue, so don't stop yet, don't terminate. Right? So it's a very simple technique. Okay? And as I said, the trivial way of doing the technique would have been forgetting all this and saying, send a broadcast query, ask everybody responds to you, just look at this, and if everybody says they're done, then system is done. If anyone says they're not done, then you say, no, that there is still work to be done in the entire distributed system. Okay? But rather than flooding the network, you basically ask only processes that have an active connection, and they ask their neighbors that have active connection. So this query is propagating through the network, and responses are being aggregated and sent back to you. Okay? So this is essentially called a termination detection algorithm that does not require flooding the network. Okay? Any questions? Yes.
What if a higher order successor dies? Like they cannot send done or continue?
That's a good question. Question is, what happens if there is a process that dies and they cannot send back? Okay? So then the technique is not going to give you a good result. And so this technique will terminate successfully and get you an answer so long as no process fails while the algorithm is in progress. Okay? Because you will not get a proper message. You will actually not get a message at all, because somebody has asked the other process, if you don't get a response, you can't reply to your parent. You are waiting for all your child nodes to tell you something before you send a response. So you will never, some nodes will not respond to you, so you'll be waiting for you. So you'll not actually find out the state of the system if a process dies while this is in progress. Okay? But we know how to deal with failures, because you can eventually use distributed snapshot, detect the failure, and restart the computation. That's a different problem, but it's a good question. Any other questions here? Okay. All right. So let's terminate. Yes, go ahead. You have a question.
I have a question from the previous slide. So when we are taking a snapshot, so what if the TCP connections are in a cyclic order? How will that be handled?
Yeah. So what is the TCP connections are in a cyclic order? So here is the exact example you asked, right? So you have A, B, and C. Okay. Each of them is connected to each of the others. Okay. You can do the exact same analysis. So let's say A starts the distributed snapshot algorithm. Okay. What is it going to do? A is going to write its state. Okay. And it's going to send a marker to B and a marker to C. Okay. Marker, when this marker arrives at B, okay, B is going to write this state, is going to send a marker back to A, because these are TCP connections, they're bidirectional, and is going to send a marker to C. Okay. Now, depending on the latency, either A's marker is going to arrive first at C, or B's marker is going to arrive first at C. We don't know how fast the network, it doesn't matter actually. One of these markers is going to arrive first. Okay. Then C will write its state to disk, okay, and then it will send markers in the reverse direction. Okay. And then let's say, for example, A's marker arrives at C first, it writes to disk, it sends a marker back, okay, and then it sends a marker to C, because you have to send markers on your connection, and it starts recording on B's channel until the marker that B has sent has already come. That marker is already in transit, but any messages before it writes to disk, when B's marker comes, it stops recording. Okay. So cycles have no problem. Okay. Depending on in the cycle which message gets to you first, it will trigger the saving your state, and then you send messages out. Okay. So it's still okay. You can deal with cycles. Cycles don't cause problems. Any other questions? But you should work out some examples like this so you can convince yourself that it actually does what it's supposed to do. All right. So I'm going to just introduce leader election. We'll continue it after the exam. I don't want to go late today. Okay, so let me explain what leader election is. Okay. So it's a class of problems where you have to elect one node as the coordinator node. Okay. Typically, we have looked at many techniques now where there is some coordinator. In clock synchronization, there was a master clock the server that kept time. Okay? And there are many other techniques that we are going to see, but there's some coordinator node. Let's say there's a load balancer. Okay? That's coordinating how requests are going to machines in a clustered web server. Okay? So you can statically choose the coordinator, but what you'll say, what happens if the coordinator crashes? Okay? You don't want a system administrator or a developer to come and say, now let's make this machine the coordinator. What if the machines could themselves elect a new coordinator? And that coordinator takes on the role of whatever the previous one did. Okay? This gets us to what is called leader election. Okay? A set of n processes have to elect a leader. Okay? And the leader election algorithm has to guarantee that only one leader gets elected. If you have two leaders, then there are two coordinators. That's going to cause confusion. Okay? If you have 0 leaders, that means there's no coordinator. Then you want to run this algorithm and pick a new one. Okay? So whenever a coordinator fails, you have to run leader election to pick a new coordinator. That's the basic idea. And that algorithm should allow you to pick some node in the system as the new coordinator. Yeah? That's called a leader election. It's a widely used technique. Anytime you need a coordinator to be chosen dynamically, you will use this technique rather than the developer saying, this is the node that's going to be the coordinator. Remember, we talked about super peers in a peer-to-peer system. That is chosen using a leader election. Okay? Time servers could be chosen using leader election. There are many such techniques. Okay? Now, in this case, there are literally hundreds of leader election techniques published. Okay? We are going to see 2 very simple ones. Maybe I'll talk about the first one and then we'll stop and continue this next time. Okay? So, you will see what is called the bully algorithm. Very simple technique. Okay? In the bully algorithm, there are n processes. We assume that each process has a unique numerical ID. We just number them 1 through n. That's your numerical ID. Okay? We'll assume every process knows the ID and the IP address of every other process in the system. That's a requirement. Okay? You know which processes are present and you know their IP address. Okay? So you can communicate with them. Okay? So the way and the communication is assumed to be reliable. Okay? That we can assume your TCP connections or communication is reliable. The basic idea in the bully algorithm is pick the process with the highest ID that is still alive as the coordinator. Okay? Very simple. Okay? So here's how it works. So essentially, any process can start an election. Okay? Any process can say, I have not heard from the current coordinator in a while. Maybe the coordinator is crashed. Let's start an election and elect a new coordinator. Okay? Here is essentially how it's going to work. Okay? You have an example here. So here there are 8 processes, 0 through 7. 7 is the current coordinator. It's crashed. Okay? 4 decides to start an election. Okay? So the way the election works is you basically send election messages to all processes with higher IDs than you. So if 4 starts the election, it has to send messages to 5, 6, and 7. 7 clearly has crashed. Right? So you will see that it's only sending to 5 and 6. Okay? So it's going to basically send election messages to 5 and 6. And every process that gets an election message is going to do recursion. It's going to start its own election process by which it's going to send election messages to higher ID processes. So 5 is going to start an election and 6 is going to start an election. What does 5's election mean? Okay, 5's election means that it's going to send a message to 6 and try to send a message to 7, which has crashed, so there's nothing to do. Okay? 6 is going to start the same election. Okay? And if you are alive, you also send a message to any previous node that sent you the election message saying okay. So you will see 4 send an election message to 5 and 6. Okay? 5 and 6 are going to send a message to 4 saying okay. Okay simply means that I am alive. We will elect a leader because we have higher ID processes than you. So sure, you are not going to be the coordinator as part of this election. Is one of the higher IDs processes. Okay, so essentially that okay message is why this is called bully, because you are bullying lower ID processes to drop out of the election. Okay? So everybody starts the election until there's only one process left. Okay? Because every process is trying to ask the lower ID processes to drop out by sending okay messages. Okay? So 5 and 6 will start the election. 5 will send a message to 6. Okay? 6 is going to send an okay to 5 and cause it to drop out. Okay? 6 will try to contact 7, but 7 is not there. So then 6 will declare itself to be the new leader. Okay? And it will send a message. Okay? So 5 sent okay to 6 sent an okay to 5, causing 5 to drop out, 6 is declared itself to be the leader and is sent I am the new coordinator a message to everyone else. Okay? So it's simple recursion where you're probing what is the highest ID process that is still there, and then those higher ID processes are telling the lower ID processes saying we will figure it out, right? You can drop out, we will figure out and tell you who the coordinator is, and you recurse until there's only one process left that is declaring itself to be the coordinator. Okay? And then you're done. Now if 7 comes back up, it can start a new election and it will win immediately. Right? Because it is the highest ID process and it can bully 6 out and start become the new coordinator. Okay? This is called leader election. There are many other techniques. We'll talk about them next time. Right? Today we are going to stop 5 minutes early, okay, and continue all of this discussion next time. So for those of you who came in a little late, okay, I posted on Piazza that the exam is tomorrow, right? So and since it was closed book and closed notes, I posted on Piazza that you can bring 1 sheet of paper with handwritten notes, which you have to then turn in with your exam. But at least that way, if you feel that there is something you not want to memorize or something like that, write it and bring it. Right? Only 1 page of cheat sheet. Right? Yes, question. You can write on both sides. Okay? So it's right. Any other questions here? Okay. So we will stop today and we'll continue on Wednesday. Good luck with the exam. We'll see you tomorrow.